Welcome, everyone. We'll just give a few minutes for everyone else to join into the webinar here. All right, everyone, we'll just give one more minute before we start the webinar. Okay, let's get started. So thank you, everyone, for attending our webinar in the Fidus Thought Leadership series of webinars. My name is Mike McCarthy. I'll be taking just a few seconds to cover some administrative stuff. We will be recording this webinar, and we will be sending a recording of the webinar out to everyone after the webinar. If you have questions about the topic, please feel free to post them in the questions area. I will be actively monitoring the questions, and if appropriate, I'll ask them during the webinar, or we'll also have some time at the conclusion of the webinar to ask those questions. If we do run out of time, we will follow up with any additional questions in a follow-up email after the webinar has been completed. So it's now my pleasure to introduce our speaker today, Dr. Syed Bokhari. Syed is a signal integrity architect at Fidus, where he has worked for over 20 years. He holds a doctorate in engineering, specializing in numerical electromagnetics, and he is the chairman of the IEEE Ottawa EMC chapter. His area of research interests include signal and power integrity, EMC, numerical methods in electromagnetics, and miniaturized antennas. He has many publications in these areas and holds 2 patents. I would now like to turn over the floor to Syed for his presentation. Thank you, Syed.
Thank you, Mike, and thank you everyone for taking time to attend this presentation. As Mike mentioned, this is a part of our Fidus Thought Leadership series. The topic we have chosen for this presentation is very useful for hardware designers and signal integrity engineers who deal with high-speed SERDES designs. Those of us who have designed or used SERDES, typically we are talking about data rates of SERDES in the range from PCI Gen 3, maybe 8 gigabits per second, going all the way up to the highest speed SERDES levels like 25 is quite common today. Over this entire range, there are issues that can range from something as simple as a high bit error rate all the way to a complete catastrophic failure. And what I'm presenting today is how does one go about debugging a high-speed SERDES problem. So we are used to doing things in a certain way, just simply to make our tasks easier. So as a result, we would use simplifications and approximations. The frequencies that we deal with for SERDES are actually in the millimeter wave range. A 25 gigabits per second SERDES has a Nyquist frequency of about 12.5 gigahertz. And if you cover up to 3 to 4 times the Nyquist frequency, we are well into the millimeter wave range. So these problems are essentially electromagnetic problems that we are solving. But to make things convenient, we would reduce these electromagnetic field problems into circuit problems where we need to deal with voltages and currents, which is what we can measure. So in this process, we end up making approximations. And one of the highlights of this presentation is questioning some of those approximations. So I will be presenting 2 practical examples here that involve actual designs which have been measured as well as simulated, and that to prove the point of how certain approximations can affect the performance of a SERDES. So before I start with this presentation, just to get some understanding of how one perceives the problem, I'll start with a simple question. Let's see. Okay, there you go. Yeah. So the question is vague, but we just want to know what your quick answer to this question could be. I have 250 ohm coaxial cables. If I connect them together, will the impedance of the new cable be 50 ohms? The question is intentionally vague. It doesn't give you a lot of detail, but we want to know what your knee-jerk reaction is, and just make a note of what your answer is, and then we'll go through at the end and see what the right answer could be. So some of you may say yes. 250 ohm coaxial cables connect together. What else can it be? Some of you may choose to say no for some reason. And a neutral answer, which in signal integrity is always used, the maybe becomes an it depends. There's never a definitive answer. So for a quick question like this, you can have multiple answers there. But if I rephrase the question into something different, for example, like this, and say, if I gave you 2 S parameter files of 2 different 50 ohm coaxial, let's say cables, coaxial, could be coaxial, and ask you to run a simulation and tell me, will the impedance of the new cable be 50 ohms? When I phrase the question in this way, it is very easy to take those S parameter files. You have one S parameter file corresponding to a 50 ohm cable. You connect it to the other file in cascade. And if you run any simulator, it will give you a 50 ohm result. So the answer from a simulation will always be 50 ohms, regardless of any conditions, because that's how the numerical simulation is done. But now let's go and look back and see what the various answers may have come from, and what is the reasoning behind the yes, no, or maybe. So those of you who may have said yes would probably assume that the cables are identical. If you take 2 identical cables of the same diameter, physical dimensions, and connect them together, the end result will be 50 ohms. There's no question about that. So those of you who may have said no would probably imagine that coaxial cables come in various diameters, some thick and some thin. And if you connect a thick cable with a thin cable, you do have a discontinuity at that point of connection, and that can lead to an impedance that is not 50 ohms. So the answer would be no, it cannot be 50 ohms. And obviously, if you went a little more deeper into this thinking and saying, so how would one connect a thinner cable to a thicker cable? They must use an adapter. If you use an adapter, adapters are generally frequency dependent. And for this reason, you would probably get 50 ohms up to a certain frequency. And beyond that frequency, it may no longer be 50 ohms. So the point to make here is simulation will always give one answer, but the reality could be three different situations that we are trying to model, which could be different. That is one point to note. The second reason is, the second point in dealing with this high-speed SERDES is that we are talking of millimeter wave frequencies. At these frequencies, most, if not all, the structures we deal with are radiate. And these are like antennas, and that's why I've taken an example of a microstrip patch antenna. So the antenna is a rectangular patch. It's a metallic patch of rectangular shape. There is a ground plane, which could represent a PCB, and the antenna is excited at one location, usually along a symmetric axis, off-centered. We will insert a ground via at some point to connect the rectangular shaped patch to the ground plane underneath it. If we measure the input impedance of this antenna as a function of frequency, we would see a result like this. It will have a real and imaginary part. At certain frequencies, it will go through a resonance where the inductive part, where the reactance goes from inductive to capacitive, and the resistance also increases. A typical microstrip patch antenna has a resonant frequency when its linear dimension is about a half guide wavelength. That's about 1.34 gigahertz here for the dimensions I've chosen. And you will see multiple resonances at integral multiples of that resonant frequency, the second resonance here. This is a normal operation of an antenna, a robust antenna. Now, if I make a small change and insert just one ground via at a corner of this rectangular patch, something entirely different happens here. The resonant frequency drops from 1.3 gigahertz to literally a quarter of the value. And this is actually a way to design miniaturized antennas. And just the point here to note is that one single ground via at a precise location can make the resonant frequency move by a factor of 4. So, and then certain resonances will be absent when you have ground vias on the patch. So in reality, this patch represents could be a power plane on a PCB. It could be anything else as a shape, and the ground plane is a large ground plane on a PCB, which is connected by decoupling capacitors to the power planes, or just a ground shape, a floating ground shape, which is connected by ground vias. So just by having a few ground vias connected to a large ground plane, you can actually change the resonant frequency by a large amount. So with this too, the takeaway message from that question I had is that when we simplify S parameters of cascaded networks, this is exact in a circuit sense. You can cascade S parameters. But in an electromagnetic sense, it is an approximation. And you need to know what it represents so that you can ensure that you're not doing a blind application of an electromagnetic problem into a circuit problem. So this is an important thing to keep in mind, and oftentimes it is possible to do that. The second thing to remember is ground plane layers, ground planes, power planes. These are all high Q they all have high Q resonances. Their frequencies have a complex behavior with geometry and ground via location. Resonances are present all the time. It's a question of whether they get excited. If a resonance does get excited with sufficient energy, then it can cause a lot of trouble. So with these two points in mind, I'll actually start the presentation now and go into those examples. So in this presentation, like we deal with, let's take a typical example of designing a high-speed backplane system. If this applies to any SERDES, where a SERDES might be running, so we may have gone through an exercise of optimization. We would model the via separately, maybe just to keep the computation time small. Pick a few nets, typically 3 to include crosstalk. Do some kind of an optimization, include connectors in the path, include traces, optimize anti-pads. We would set up these various elements, blocks, simulate them separately, include the manufacturer specified data where available, and construct a circuit diagram like what I've shown here. Then once the link is established, these are S parameter blocks that are concatenated. Some of these we might want to introduce a PN skew in the differential pairs by adding a transmission line to represent maybe fiber weave skew. And we would compute the insertion loss of the whole link, maybe run it through an eye diagram simulation to obtain a result. Now, just pay attention to this slide, and then I'm going to show you the next one. Okay, so these two slides are literally identical, but they have a small difference. The difference, as you can see, is that each of these blocks, S parameter blocks, has its own ground reference, which is when we determine the S parameters of a block, we don't know exactly what it connects to, but it has its own ground reference. When we hook them up together, we are actually hooking up the grounds as well. Although we don't see it very clearly in a schematic like this, we assume that the grounds are also connected exactly. And this is where the assumption is very critical. So let's now see what are the kinds of SERDES issues that one encounters normally. So we say a common problem is that the multi-board system has an unacceptable bit error rate at say 25 gigabits per second. So which means that the error has exceeded the 10 power minus 14 or some standard, some metric that we're trying to hit. This is a common problem, and then the solution is to find out the problem is to find out why it is so and see if it can be if either the bit error rate can be improved or just brought down to 0 if it's possible. So I have an example of this. Now the second example is that the system works at 10G. This is a very common one which you may have seen. The system works at 10G at 10 gigabits per second, but fails to operate in the extended mode of extended 10G base KR. So the design could be that the design has a low margin, which is why just increasing the data rate by just 1 gigabits per second is making it to fail. So sometimes you might, oftentimes people want to use the same system to run at a next generation. Like for example, PCI, a system that was designed for PCI Express Generation 3 with very little changes, just changing the silicon and trying to run it at for Gen 4. It sometimes could be possible if the Gen 3 had a lot of margin, but it's probably not likely to work at Gen 4. This is another kind of an issue with the SERDES. Now, the more complex ones are these. These are the ones that can cause a lot of grief. 8 out of 10 boards appear to run error-free. Yeah. Potentially, this is an indication of board-to-board variation. Could be a fiber weave effect. Now, these are the real killers. All lanes except 2 run error-free at 25 gigabits per second. That is one that's extremely hard to debug because you'd wonder everything looks almost the same. And then all of a sudden, why do two lanes fail to operate properly? This is a really interesting one, and it is real, although it may sound funny. It appears to work fine when I press hard on the connector. Yes, this is, for those of you who have worked with the QSFP module, just try it out in the lab. Try to retract the QSFP module a little bit, just a little bit, not a complete disconnect, and see what happens to the errors. The errors can sometimes get better or sometimes they get worse. And then when some of those who just give up on this, finding it out, they said, oh, it could be because there's missing ground planes, there's too many split plane power planes are being used. Let's add a lot of ground planes and a lot of ground vias, and those who are lucky, the problem just goes away like that. So we can encounter any or all of these combinations of SERDES issues in reality, and the finding solutions for the first type of problems, it could be simpler, mostly a margin issue. The last categories, these three in the red, are usually very, very hard to debug. And we'll present here a theory that can explain why sometimes you see these variations. Now, when we design this, just a quick refresher on the parameters of interest. The S parameters that we deal with are typically you have a skew between the P and N diff pairs. We highlight that as being very critical. It is not a fundamental parameter, but it affects all the fundamental parameters. The most fundamental one we would consider is the insertion loss. Insertion loss is the energy that's lost over the link. Then you have return loss, which is the reflected energy. And then you have crosstalk, which comes in two types, usually the far end crosstalk and the near end crosstalk. These would be identified as the fundamental S parameters, and IEEE has specifications on these on what they are. Now, if in this diagram we try to simplify them, so in a system, almost everything affects the skew, which is the fundamental parameter. The PCB material traces can never be straight; they have to be bent. They contribute to a skew. Vias contribute to a skew, can contribute to a skew. You have capacitors. Sometimes on the differential pairs, they need not be identical, exactly identical. They can contribute to a skew. The breaking out of the traces near the BGA region is never identical, so that can result in a skew. Almost all connectors will have some amount of skew in them, and you have the stack up as well, which can cause skew because of the material or any of these things. And all of these will affect the fundamental parameters: insertion loss, return loss. Now with these two, and then the crosstalk. Once we use the crosstalk, we define an insertion loss to crosstalk ratio. And the insertion loss variation is also specified as an insertion loss deviation. So these are the parameters that the IEEE, for example, 10G base KR used in the beginning. We still continue to use this, although there are a few more evolved ones, such as COM and effective return loss these days. Yet the fundamental ones remain the same. Okay. So we would usually use a flowchart to design, and while debugging, we just use the same flowchart and go backwards. So just see if everything is met. Typically, this is when you're dealing with a long link, and it's almost always the case in high-speed SERDES. Your frequency of interest is primarily what we call the Nyquist frequency, which is just half the data rate. So 25 gigabits per second, we are looking at a 12.5 gigahertz Nyquist frequency. We look at the parameters at this frequency because if the link is long, and even if a pulse is transmitted, it will look like a sine wave eventually. And so it is good. It is enough to deal with the Nyquist frequency, the first Nyquist frequency. Sometimes we may want to go up to 2 to 3 times Nyquist, but it's quite rare. So at that frequency, we calculate the insertion loss, and we can check and see if the silicon devices that are used can transmit this amount of energy and receive it as well. If they cannot, then you would probably use a retimer or a redriver in the circuit, and then go through all the other IEEE requirements to see if they're satisfied. Then maybe do an eye diagram simulation, do some optimization, and that gives us a link that could meet an error-free operation. So when we have a problem, it is possible that if there's a problem where the devices the data rate of the devices can be changed, and this is especially true when we are using FPGAs. When you're using FPGAs, the data rate can drop, can be varied. We could find out if a link does not operate at 25 gigabits per second, does it operate at a lower speed, a lower data rate, maybe 16 or maybe less? That is already an indication that there's a signal integrity problem. Now, another test would be where it's possible, again with FPGAs, can you operate with a lower pseudo-random bit screen, like the PRBS7 pattern? And does it work error-free with that pattern? The pattern also determines the frequency of the bit variation, and that's another test to do. And another test, very useful test to do where it's possible, is to enable and disable lanes selectively. Now, if we have a number of lanes and we disable all except one, and then the operation is robust, and then as soon as we turn on another lane, it starts giving errors, then we know that there's a crosstalk effect. These are easy to debug when the devices use our FPGAs, because they invariably provide these a variable data rate, a variable data pattern capability, and the ability to enable and disable lanes. But in general, it is not possible. So let's start with a problem. This is the standard application involving QSFP modules. It could be an FMC type of application where you have a large board with a number of ASICs or FPGAs that are hooked up through a connector to a number of QSFP modules, let's say, a number of them. They might be running a 25G COWI, in which case we also have insertion, precisely determined insertion and insertion loss budgets, about 10 dB or something in this case. So here a common problem is again errors appearing on one or more of these QSFP modules. So there's one problem which we debugged here. We did a measurement actually with a system that had a similar, the system worked, but it had lots of errors. So when we simulated and measured the link from the end to end, we saw that it was exceeding the 10 dB insertion loss requirement by about 3 dB. And it also had a very high return loss at the fundamental frequency. Look at the return loss. It was almost like a dB down, so which is extremely high. And as a result of this poor return loss, we also got a very bad insertion loss deviation. If you see this, the way this the insertion loss curve is, it should ideally be a straight line. The way it is oscillating, it increases the insertion loss deviation. So the result was an I that is very marginal, and which is clearly what led to bit errors. So the solution in this case was to use a better PCB material and improve on the insertion loss and do some optimization to improve on the return loss. It was not possible to do the optimization to the fullest extent. And so we ended up with some improvement on the insertion loss by using a higher quality material. But the return loss was marginally improved. And with this, once we simulated it, you can see that the eye diagram, the eye opens up very nicely. And it passed these lanes, all those failing, the high error data lanes was rendered error-free. So fairly easy, it's a relatively easier problem to debug and determine. It's a question of high insertion loss deviation and not meeting the margin. Now we'll talk about the more interesting, the critical problem, the problem where the answer is not very obvious. So when we cascade networks, we make the implicit assumption that the reference plane, the reference ground is of both the parts of the network has a very low impedance connection. This connection is implied, and we see the impact of this in the next example that I'll show. So here's an example of a very simple structure, but just mostly to prove the point. So I have air dielectric. I don't want to complicate anything here. We have two rectangular pieces of copper. Three of them actually. A is a wide-shaped rectangular piece of copper. B is a very thin and narrow strip, and C is almost identical to A, but with an except it's longer. And we have one microstrip line running from end to end. It's traversing all the three regions A, B, and C. So we solve this problem in two different ways. In the first method, we take the section A and just take the part of the transmission line that is above the plane shape A, solve it separately, get its S parameters. Take the section B, take the part of the line that is above the strip B and get its S parameters. And take C and do the same thing. That is one way of solving. And then to do the end-to-end S parameter, the insertion loss going from end to end, we concatenate or cascade those three S parameter blocks, like we do with S parameters. That is solution one. The second solution is to do a full 3D EM simulation starting from the end of the trace on A all the way to the end of trace on B. There is just one simulation being done, including all three objects. So if you see the result of the S parameter simulation of three concatenated blocks, the insertion loss shown by the red curve. It's nice and smooth, and it doesn't show anything unusual. But the rigorous solution of the full 3D EM, it shows that there is a resonance happening within this frequency range. You can see this resonance clearly. Just note the scale. The scale is actually very small. This resonance is not very pronounced. If I plot these two graphs on a 40 dB scale, they will probably look the same. You can barely notice this, but this can get much worse. So now let's see why this might have been happening. So let's define something called a ground impedance. Just the reference plane here has two ground shapes connected by a thin strip. Maybe we can call something a ground impedance. And what we do is we take the rectangular shape, like let's say the first example. We have a very thin strip connecting these two rectangles. We put an excitation here at the point of connection, assuming that that's some kind of a delta gap excitation to calculate the impedance of this source. If I had a source here, what would be my impedance? So if I do the simulation using a 3D field solver, I'll see that it has resonances, and the return loss of this is not exactly smooth. It has multiple resonances. So I'll increase the ground. I'll add more strips along this region to increase the number of ground connections, let's say. And then when I added about 3 strips, it improves quite a bit. And then my return loss gets closer to 0 dB, which it should, because I'm trying to get a perfect shot. And lastly, I'll add a lot more of these strips, and that brings the return loss close to 0 dB, meaning that it's a perfect shot. It will become perfect shot. So you can see here is that the ground planes can have an impedance, which can also resonate. And this is why this result gets affected. the actual insertion loss gets affected due to the ground plane resonance. So yeah, so this is the with this we have to we'll see how we will use this technique to determine what the problem was. I'll explain briefly a problem. Okay, this is a board. This is a system that we designed and manufactured as well. It's a product called Sidewinder. It has an FPGA, which is the source of the SERDES. It has a number of SERDES interfaces going all the way from 8 gigabits to 25 gigabits. The one particular one that posed a challenge was the NVMe Express module. This is usually a very small PCB, a very small module that is mounted on this board. It has a very simple connector too. So what happened here was we were running this at 16 gigabits per second, and a couple of lanes were showing a high error rate. They were functioning. They were showing a high error rate. It was a bit random, and we wanted to know what was causing it and why was it only happening on those 2 lanes. So in order to do this simulation, we went back to the way what was explained before. We took the SERDES, we took the connector and modeled the connector as a connector, NVMe module, and a part of the main PCB as one entity. We didn't do any concatenation of S parameters here, although after the small part of the main PCB, we connected it to the SERDES through the S parameter again. But this is a very long trace, and it would take a very high computing time to simulate. So if you look carefully, if I try to zoom in here, there's nothing unusual about the routing or the connection to explain why two of the lanes that had errors, they actually looked similar to the other lanes. There were some differences. There's one of them had a 0 ohm resistor connected between the ground and another pin, and that was one of the things. So when we did this simulation, okay. So when we did the simulation, we computed the return loss and the insertion loss deviation. Again, we're suspecting as soon as we look at a return loss, it was showing a lot of variations. It wasn't exactly less than 10 dB as one would normally expect, and that would affect the insertion loss deviation, which is basically the deviation of the insertion loss from a straight line. And we noticed that it is quite a bit high, like our fundamental frequency is like 8 gigahertz, that link of operation for 16 gig. This is about, it exceeds 4 dB. I mean, this typically the IEEE recommended value is about 2 dB. So there's a very high insertion loss deviation, which is one thing to address. And then we're trying to find out why would you get such a high insertion loss deviation. So then we looked at the insertion loss of the link along with the single-ended insertion loss of the P trace and the N trace. This on the link that had most errors. So we see that the single-ended insertion loss has a resonance around 6 or 7 gigahertz, a sharp resonance. When you do a differential, it reduces a bit, highlighted here by this figure. This has the resonance is present. This simulation also assumed first that both the P and the N signals are in phase. That is what would be, I mean, the P and N signals have no skew between them. So which is why the curves are almost the same, identical. Now we also looked at the ground impedance. In this case, we have a ground being connected by these ground pins, and including that 0 ohm resistor which is connected. So the impedance of the ground structure of this small board as well as the large board at the point of connection. The only connection between the ground between the small PCB and the large main PCB is through these ground pins, and they were modeled using a solid model. And when we look at that, we see the ground also had a lot of resonances. And I plotted here the ground resonance versus the insertion loss. Some of these resonances actually are quite close to where we see those dips in the insertion loss. Some are not. This is again, like I said, is a fairly complicated complicated thing to correlate, and some are fine too. Some don't even show the effect. Now, when we measured the eye diagram using the FPGA utility, the eye diagram of the eye scan of the high bit error rate lane showed a very small eye opening, and the other lanes that seemed to work well, they had an eye opening that was much better. So this was to illustrate what's happening over here. And so when we do this, when we simulate this with a Z, if there was no skew between the P and N lanes, with a zero skew, we saw that we don't see the eye as being closed. Like, so with a 0 picosecond of skew, the eye is there's a bit of errors. There's a few errors, but the eye is still open, so that means you can get many bits through. But what we don't know in our system is what is the amount of skew between the P and N. We used a high quality substrate material, but yet it was also single ply material. You can, from experience, we know that even with a single ply, even a spread glass weave, spread glass weave style, you can get 2 picoseconds of skew per inch quite easily. So if we assumed over the length of the trace, we got a 20 picosecond skew. If the skew was in the unfavorable direction, the resonance dip that I'm plotting here, which is around 6 gigahertz, will actually improve. And if it is in the unfavorable direction, depending on whether it's P skewed with respect to N or N with respect to P, it can get worse. So you can see that if I use the 20 picosecond skew that made it worse, the eye diagram would simply close. So what was happening in this case was a question of a combination of fiber weave skew and a weak ground connection. So in the next revision of this printed circuit board, we increased the ground via connections here by I don't have a picture, but yeah, we increased the number of ground vias connecting, used double ground vias, and removed these 0 ohm resistor connections, and ensured that there was the ground connection was made as robust as possible. And with that, the errors went away, and we had boards now. All the boards that we make now, a number of them do not have this issue at all. So with that, I'm coming close to concluding our observations here with respect to the debugging of multi-board SERDES issues. So the SERDES links are affected by reference plane resonance. Okay, this can happen in many cases where the connectors that are used are not necessarily the best quality connector. In backplanes, this is not so common because with backplanes, every pair has at least 2 adjacent ground pins and a lot more as well. And the way those connectors are designed, they do connect the daughter card, a line card reference plane is very well connected to a backplane, and the likelihood of resonance is much smaller. But in the case of simple modules like QSFPs, SFPs, NVMe modules, the ground pin connection is limited, even though every pair has 2 ground pins on the sides. It's important to ensure that there is a low impedance connection between the small PCB and the motherboard. So this is caused, so when this is not done, the reference planes have a weak connection and they'll resonate, and they resonate. The resonance can be strong or not, but more than the resonance is the resonance combined with a fiber weave skew. When there's a fiber weave skew present between the P and the N traces, that is what can make things really worse. And fiber weave skew is inevitably present in almost every board. So precautions we'll see about once we have a skew and resonance, things can happen leading to a variation in performance. So how do we mitigate this? Again, increase ground pins in the multi-board connector as much as possible. There is no such thing as overgrounding and overkill. You can have 2 ground vias if they can fit in the space, put 2 ground vias. Never, never, ever use a thermal breakout on the ground on a reference ground via. I've seen that in many designs. That is not. A ground via should have a complete 360-degree connection to the ground plane. Okay. Some designers tend to think that it'll be very hard to solder and desolder. No, it's not. That's not an issue. Ground via connection to the ground plane must be a solid connection to give the lowest impedance. Increase ground vias and PCBs on both sides of the connector. Again, this is very critical. Even though it's a small PCB, we use as many ground vias as possible to eliminate this one. Routing symmetry is also important near the connection discontinuity. That's where there's a discontinuity. If you maintain very strict PN routing, try not to do the skew matching near the connector, or maybe a little away from it is better. That way you will not excite a common mode current, which will excite a resonance. And clearly, do as best as possible to reduce the fiber weave skew. Many techniques exist in the literature there for fiber weave skew reduction, and one or more of them should be used all the time. So when we made these changes in our product, which we usually produce in quantities of 50, we saw these problems go away, and this is now we have all lanes working error-free all the time. So with this, I'll conclude my presentation. I hope this information is useful to you. And if you have any questions, I'll be happy to answer them.
Syed, thank you. That was a fantastic presentation. We received 2 questions during the webinar. The first question was from John. Is it possible to run 25 gigabit data on low-cost PCBs made from using materials such as FR4?
Yeah, that's a very good question. Yeah, as we see these days, it's very common. Cost reduction is almost every product. The first thing that seems to come that seems to be indicated as a constraint is low cost, low cost, low cost. It always has to be low cost. Even in the case of like 10 gigabits per second SERDES, we have seen that what used to be done on very exotic materials is commonly done today using low-cost PCBs. So for certain frequency range, certain data rate ranges, we have used routinely the lowest cost FR4, for example, on SDI type of interfaces, that's 12 gigabits per second. We use FR4 materials. And these devices also have a very high dynamic range. They can, the silicon can handle about 40 dB of insertion loss. They're usually meant for long video cables. So yes, in the case of certain SERDES, even operating up to 12 gigabits per second, you can use low-cost materials FR4. At 25 gigabits per second, it's a challenge. The reason being that the loss on a FR4 like PCB at 12 gigahertz, fundamental at 12 gigahertz it's typically in the range of exceeds 2 dB per inch. And whereas on a very high quality material, it could be less than 1 dB per inch. So if you have 2 dB loss per inch, and you have a 25 gig SERDES, and you have a trace running about 5 to 10 inches, that's already a lot of loss on an FR4. So in that case, it would not be possible to use a low-cost material for 25 gigabits per second operation. But if the link is very short, it's possible. Like the example I showed, the first example I showed there, the link was not very long, but it's very easy to quickly eat up 10 dB with a low-cost material. If everything is done properly and you're within the link budget, you could use FR4 as well. Yeah. Okay.
Excellent. We got one more question. Which of the S parameters play the most important role in a long reach application?
Yeah, that's again another good question, because the S parameters, like I said, we do have if I go back to the slide, it's we have these the fundamental parameters that are there, but there's not a lot of them, but it's yes. So there's now primarily we treat the insertion loss as the most important one, because almost every standard has a limit, and we know exactly how much it can support. So for example, I mentioned the SDI links, they can deal with 40 dB, but they're actually single-ended and they're not differential. Now, in most of the other differential applications, the insertion loss specification could be in the range of 20 dB or so. So we would treat the insertion loss with the highest importance. The next one could be the return loss. We have seen here, like in this example that I showed, the return loss was really bad, like 1.5 dB, and this still worked. So we wouldn't consider the return loss to be so critical as a parameter, but it would be crosstalk would be the next one. So I'd probably say go with the insertion loss being the highest priority. The next one is crosstalk. Crosstalk is the one that will remit a long range application. For example, mostly this what we call as the near-end crosstalk. So if the link is very long, the received signal would have attenuated substantially by the time it hits the receiver. And if the transmitter is very close to the receiver, it can swamp the receiver. So near-end crosstalk would be the next, far-end crosstalk probably the third, and we'll put the return loss as the last choice. That would be the order in which we'd go. But again, this answer is debatable. Some people would probably give more importance to return loss, probably the last one to crosstalk. So it's one of those where it depends type of situations. So insertion loss, if you ask me, it's insertion loss, near-end crosstalk, far-end crosstalk, return loss, in that order.
Excellent, thank you. We did not receive any other questions. If anyone does have questions, please feel free to follow up afterwards. As I mentioned earlier, I will be sending the webinar recording out. It'll also be hosted on our website, fidus.com, in perpetuity. So if anyone wanted to use it as a resource, that will be posted shortly. We have more webinars coming up in our Fidus Thought Leadership series. Please feel free to have a look at your email and sign up for any of those. They're just free resources that we're trying to, highlight some of the great skills and abilities that we have here at Fidus, and we'd love to have you participate in those as well. Thank you for your time today.
Yeah, thank you, everyone. Thanks, Mike. Thanks, bye.